Today, we're going to talk about Wireshark, a super handy tool for checking out what's happening on networks. It's like a secret agent that can spy on all the data going through a network, helping us understand how things work behind the scenes. In this guide, we'll cover everything you need to know about Wireshark, from getting it on your computer to using it to see what's going on in your network. Whether you're a hacker or just curious about how the internet works, Wireshark can teach you a lot about the magic of data flowing through networks. So let's jump in and explore Wireshark together. Alright, let's kick things off by talking about Wireshark. Wireshark is like a detective tool for computer networks. It's free software that lets you peek into the data flowing through a network in real time. Whether it's data traveling through Ethernet, Wi-Fi, Bluetooth, or other types of connections, Wireshark can capture and analyze it all. You can use Wireshark to figure out what's happening on your network, troubleshoot issues, or just learn how network protocols work. It's super handy for tech pros, security folks, and even students studying networking. Now, let's dive into some cool things Wireshark can do. Wireshark works on all major operating systems. Whether you're using Windows, Linux, Mac OS, or Unix, Wireshark has got you covered. Live packet capture. It can capture data as it's happening on the network, giving you real-time insights. Analyze data from other tools. You can analyze data captured by other tools like TCP dump, WinDump, or Tshark. Import and analyze hex dumps. If you're into the nitty-gritty details, Wireshark can handle hex dumps like a champ. Export data in different formats. You can export captured data in various file formats for further analysis. Detailed packet analysis. Wireshark can show you detailed protocol information, filter packets, colorize data, and even search for specific packets. Create statistics and graphs. It's not just about capturing data. Wireshark can also create graphs and stats based on the captured packets. Decode encrypted data. It can decode encrypted data if you have all the necessary information. And that's just scratching the surface. Wireshark is a powerful tool with a lot of features that can help you unravel the mysteries of network traffic. If you want to download Wireshark in Windows or Mac, you can get it from their website. Just visit the site, choose your operating system, and the download will start automatically. If you face any challenges while installing Wireshark on your operating system, don't worry. You can always research solutions online or ask me in the comments section. However, if you're using Kali Linux, you don't need to download Wireshark separately because it comes pre-installed. For those who don't have Kali Linux, you can check out my video guide on how to install it. I've included all the links in the video description, so don't worry about missing anything. To open Wireshark on Kali Linux, you can follow these steps. First, go to the Applications menu in Kali Linux. Look for the sniffing and spoofing section, and you'll find Wireshark there. You can open Wireshark directly from this menu. Alternatively, if you prefer a quick method, just open the command terminal. Then type Wireshark. It's as simple as that. Now, let's choose the interface you want to capture. You'll see a list of interfaces available, some of which may look useful but aren't relevant for our video. Don't worry about those, just pick the interface you want to capture data from. The best part: Wireshark does the detective work for you by automatically detecting and listing the interfaces that are active and ready to capture data. So, simply select the interface you're interested in, and Wireshark will start capturing the network traffic flowing through that interface. So, go ahead and choose the interface that intrigues you, and let's uncover some fascinating insights into network traffic. Before we begin with Wireshark, it's essential to understand network protocols. Think of network protocols as the languages computers use to talk to each other. Knowing about these protocols will make using Wireshark a lot easier. If you're not familiar with network protocols or need a quick review, I have a video explaining networking protocols. It'll give you a good foundation in networking. Before we dive into capturing our first set of data with Wireshark, let's take a moment to become familiar with its interface. Firstly, there's the menu bar, which acts as the central command center for all the tools and options within Wireshark. It's like the control panel of a spaceship, allowing you to access different functionalities neatly organized, much like navigating through the Applications menu on your computer. Next up is the toolbar, functioning as a quick access toolkit. This toolbar houses commonly used tools, making it easy to find what you need without the hassle of searching through menus. For instance, you can stop capturing or restart captures with just a click. There are also options for automatically following live capturing and more. Next up, we have the filter feature. This is where you can type in specific criteria for what you want to see, and Wireshark will filter the captured packets accordingly. It's a powerful search tool at your fingertips, allowing you to focus on the packets that are relevant to your analysis. For example, let's say you're interested in only HTTP traffic. You can simply type HTTP in the filter box, and Wireshark will show you all the packets related to HTTP communication. This makes it much easier to narrow down your focus and extract the information you need from a large dataset of captured packets. Filters in Wireshark are incredibly versatile and can be based on various parameters such as IP addresses, protocols, ports, packet types, and more. It's a handy tool for pinpointing specific network activities and troubleshooting issues efficiently. As we move along, we encounter the packet list pane. This pane serves as your window into the vast network world. It displays a comprehensive list of packets captured by Wireshark as they travel through the network, giving you a visual representation similar to observing a stream of data flowing by. When you select a packet from the list, the packet details pane becomes your treasure trove of information. It's like peeking inside an envelope to unveil its contents. Here, you'll discover details such as the packet's origin, destination, and the protocols it uses for communication. Now, let's delve into the technical aspect with the bytes pane. This pane reveals the actual data within the packets, showing hexadecimal bytes and their corresponding ASCII values. It's akin to decoding a secret message as it travels through the network, revealing the hidden information. Finally, at the bottom of the interface, we have the status bar, acting as your assistant providing real-time updates. It offers valuable information such as the total number of packets captured, capture duration, and other essential details about Wireshark's activities. This quick overview of the Wireshark interface provides a solid foundation for diving deeper into its functionalities. As we progress in this learning journey, we'll discuss each option in more detail. So, imagine you've selected the right interface in Wireshark, but then you look at the packet list pane and nothing. No packets in sight. It can be a bit frustrating, right? Well, there are a few reasons why this might happen. Firstly, there might not be any network traffic happening at that moment. It's like trying to catch a bus when there aren't any running. Secondly, the packets moving through the network might not be meant for your device, so Wireshark doesn't grab them. It's like trying to eavesdrop on a conversation that's happening too far away. And finally, there's this thing called promiscuous mode. If it's not activated or available in your settings, Wireshark won't capture all the network traffic. Now, when you fire up Wireshark, it might not look super exciting at first glance. But trust me, it's the packets that are flowing around that make it fascinating. Yep, we're talking about capturing packets. That's where the real action is. Alright, let's start our first capturing session. Now that you've got a grasp of the basics of Wireshark and have learned how to install it, I believe you're all set to dive into your first capture. In this section, we're going to walk through initiating your first Wireshark capture. We'll also cover how to save the captured data for future analysis or to share it with others. Alright, let's get started by opening Wireshark. Once Wireshark is open, you'll see a list of available interfaces to capture data from. In my case, I'll choose N0, but keep in mind that this option might not appear for you if you're not using a wireless network adapter or if your system has different interface names. So, go ahead and select the interface that corresponds to your network setup. Now, you might notice some packets appearing in Wireshark's packet list pane, or you may not see any activity if there's nothing happening on your interface. To test whether Wireshark is capturing data effectively, let's open a browser and search for something. Once you start browsing, Wireshark should start capturing the data packets related to your browsing activity. If you see packets being captured, then well done. You've successfully captured your first set of data using Wireshark. As you can see, there's a lot happening within these packets. But don't worry, we'll dive into understanding these packets later. For now, let's focus on the fact that we've successfully captured data for the first time. Now, let's see how to save these captured packets for later analysis or share them with someone. Simply click on the save icon, and a window will pop up asking you to choose a file name. You can give it any name you prefer. By default, Wireshark saves the file as a PCAP-NG file format, but you also have the option to choose other file types like PCAP or others depending on your needs. This way, you can store and share your captured data easily. Okay, now, I encourage you to pause this video, open Wireshark, capture some packets, and save them with a file name of your choice. Once you've done that, you can come back to this video and continue watching. Capturing packets and working with Wireshark hands-on is a fantastic way to reinforce your understanding and skills. So, go ahead and give it a try. I'll be here when you're ready to continue. Now, let's delve into the different filtering options available in Wireshark. We'll also explore how to create and use different profiles to enhance your packet analysis experience. In the world of Wireshark, filters play a crucial role in refining your packet analysis. They allow you to see precisely what you want to see and capture only the data that's relevant to your analysis, making your workflow more efficient. There are two main types of filters in Wireshark: capture filters and display filters. Let's begin with capture filters. This feature gives you the ability to capture specific packets while discarding others. Capturing packets can be resource-intensive, requiring significant processing power and memory. Therefore, using capture filters helps conserve resources for other tasks and ensures that you capture only the data that meets your criteria. On the other hand, display filters work differently. They don't discard any packets, but instead hide packets that don't match your filter criteria. This makes viewing and analyzing the captured data more convenient. It's important to note that once packets are dropped due to a capture filter, they cannot be recovered, which is why it's crucial to use display filters judiciously. When you apply a display filter, only the packets that meet your filter specifications will be displayed in Wireshark. You can monitor the number of packets being displayed after applying a filter in the second column of the status bar in the Wireshark window. Understanding how to use capture and display filters effectively can greatly enhance your packet analysis capabilities and streamline your workflow in Wireshark. Let's explore these filters further to maximize the insights gained from network traffic analysis. Before we dive into demonstrating filtering options in Wireshark, I want to introduce you to a comprehensive filtering guide. Unfortunately, I can't cover all the filter options available in Wireshark in this video, but fear not. I have an excellent cheat sheet from Station X that will provide you with a wealth of filtering techniques. This cheat sheet is incredibly helpful and covers various filter options that you can apply in Wireshark. It's a fantastic resource to have on hand, especially when you're dealing with complex filtering scenarios. I'll include a link to download this cheat sheet in the video description. I highly recommend reading through it and using it as a reference while working on your network analysis tasks. Let's explore some common filtering options in Wireshark. Imagine you're interested in just TCP traffic. In Wireshark, you can simply type TCP in the filter bar and voila, it'll show you only TCP packets. This is super handy for analyzing things like web browsing or file transfers. Similarly, if you want to focus on UDP packets, like those used in video streaming or VoIP calls, just type UDP in the filter bar, and Wireshark will filter out everything else, showing you only UDP traffic. Now, let's say you're troubleshooting a web server issue. Typing HTTP in the filter bar will narrow down the packets to just HTTP traffic, making it easier for you to spot any anomalies or errors. Let's say you're curious about the communication between your computer and a specific IP address, say 192.168.1.1. Typing IP.ADDR == 192.168.1.1 in Wireshark will filter the packets, showing you only the ones involving that IP address. You can also filter based on MAC addresses. For example, if you're troubleshooting a network device with a specific MAC address, typing ETH.ADDR == MAC address you want will highlight packets related to that device. Ports are crucial for network communication. If you're interested in HTTP traffic, which usually uses port 80, just type TCP.port == 80 to focus on packets going through that port. Similarly, if you want to examine DNS queries often using port 53, you can use udp.port == 53 to filter out everything else and see only DNS-related packets. Wireshark also supports logical operators like AND, OR, and NOT for more complex filtering. For instance, you can combine filters using AND to see TCP packets with a specific IP address, like TCP port == 80 and IP header == 192.168.1.2. The OR operator lets you specify multiple conditions. For instance, TCP port == 443 or TCP port == 80 will show TCP packets using either port 443 HTTPS or port 80 HTTP. Finally, the NOT operator is handy for excluding certain packets. For example, NOT IP header == 192.168.1.100 will filter out packets involving the specified IP address. Playing around with these filters in Wireshark can help you dig deep into network traffic, troubleshoot issues, and gain valuable insights into your network's behavior. Wireshark offers a handy feature for enhancing our viewing experience through colorization of traffic. This feature allows us to highlight specific types of traffic with different colors, making it easier to distinguish between different sets of data. The purpose of colorizing traffic is akin to finding a needle in a haystack. By assigning different colors to various types of traffic, we can quickly spot and focus on the traffic that's most relevant to our analysis. By default, Wireshark provides colorization rules for most protocols, which is why you might already see traffic displayed in different colors in the packet list pane. You can access these default color rules by navigating to View and then clicking on Coloring Rules. For instance, Wireshark may colorize bad TCP traffic differently to draw attention to potential issues or anomalies in TCP communication. If you want to add your own colorization rule, simply click the plus icon in the Coloring Rules window. Then, specify the filter criteria you want to use for colorization, such as TCP port == 80 for HTTP traffic, and give your color rule a descriptive name. You can also choose the color you want to assign to this rule. With colorization in Wireshark, you can customize your analysis environment to highlight specific types of traffic, making it easier to identify patterns, anomalies, or critical data within your network captures. It's a powerful tool for improving visualization and analysis workflows. Okay, now one great feature of Wireshark is the ability to use profiles. Profiles in Wireshark are like personalized setups that can save you a lot of time when analyzing a network. A profile includes various components such as capture filters, display filters, time preferences, column preferences, protocol preferences, color profiles, and more. These components work together to create a customized environment tailored to your specific needs for network analysis. Importing and exporting profiles in Wireshark is straightforward, which is incredibly helpful when working on different networks or systems without your usual tools. You can simply copy and paste the profile configuration files into a specific directory to use them. Here's how you can create a profile in Wireshark. Right-click on the profile column in the status bar. Select New in the pop-up dialog. Give your new profile a name. Click OK to create the new profile. Once you've created a profile, you'll see it activated in the status bar. Any changes you make within this profile, such as creating capture or display filters, adjusting protocol preferences, or changing color settings, will only apply to that specific profile. This means your changes won't affect other saved profiles. By using profiles, you can set up different configurations for specific network analysis scenarios. This flexibility not only saves time, but also makes your tasks more manageable and efficient. Wireshark provides a wealth of statistics related to packets and protocols involved in network communication between hosts. These statistics range from basic metrics to advanced and specific details about the protocols being used. Let's discuss some of the most useful tools available in Wireshark's statistics menu that can help us gain better insights into handling complex network situations on a day-to-day basis. Alright, So the first here we're diving into is the capture file properties. This tab is like a treasure trove of information about the packets you've captured. Here you'll find file. Firstly, when we talk about file properties, we're looking at basic details like where the file is located, how big it is, and some unique and this hashes that help identify the file uniquely. Now, onto the time aspect. We're interested in knowing when the first packet was captured and when the last packet was captured. The elapsed time tells us that the capture lasted for what time. Next up, the capture section tells us about the hardware, operating system, and the software used to capture the data. For example, it mentions an Intel Core i7 processor running Linux, and it was using Wireshark version 4.2.2 to do the capturing. Moving on to interfaces, it's about the specifics of how the data was captured. We're talking about the network interface used, whether any packets were lost during capture, here it's marked as unknown, if any specific filters were applied during capture, here it's none, and the type of network link used, along with the maximum size of packets captured. Lastly, the statistics section is where we get into the nitty-gritty of what was captured. It tells us things like how many packets were captured in total, how many were actually displayed or analyzed, the duration of the capture, and averages like the rate of packets captured per second, the average size of packets, the total number of bytes captured, and the average rates of data capture in bytes per second and bits per second. And if you've added any notes or comments while capturing packets, they'll show up here. It's a great way to jot down observations or reminders for later analysis. You can add comments and save them. So, all this information together gives us a comprehensive view of what was captured, how it was captured, and some statistics about the captured data. And now hear the end. Resolved addresses refers to the process of converting network addresses from their raw format like IP addresses or MAC addresses into human-readable names, such as domain names or device names. This conversion is done using various protocols like DNS for IP addresses and Address Resolution Protocol for MAC addresses. This feature is particularly helpful when trying to identify devices, servers, or websites based on their network addresses. For example, instead of seeing an IP address like some IP address in the capture, Wireshark can resolve it to a hostname like google.com if a DNS lookup was performed and the IP address was mapped to that domain. Similarly, for MAC addresses, Wireshark can resolve them to device names if ARP requests and responses were captured, allowing you to see something like device name instead of just a series of hexadecimal numbers. Now in Protocol Hierarchy window provides us with an overview regarding distribution of protocols used in the communication process and how to spot unusual activities in your network that do not follow the benchmark as expected. It's your personal tour guide through the jungle of network protocols. Protocol Hierarchy acts like your lookout tower, giving you a sweeping view of how data moves between hosts. It's like having a radar that scans for any weird stuff happening in your network. It breaks down all the different types of protocols being used and shows you the percentage of each one. Plus, it gives you stats like how many bytes and packets are flying back and forth. It's like taking a snapshot of who's chatting with who and how much they're saying. And here's the cool part. You can use Protocol Hierarchy to dive even deeper into specific types of traffic. Just right-click on a protocol, hover over Apply as Filter, and click Selected. It's like putting on a pair of super-powered glasses to zoom in on the stuff you're interested in. So, let's say you're a bit worried about one particular host in your network acting a bit funky. Protocol Hierarchy comes to the rescue. It helps you pinpoint exactly where that strange behavior is coming from and get to the bottom of things. Alright, let's talk about the conversations window. So, picture this. You've got this massive network with tons of devices all chatting away. Now, normally, devices are meant to talk to each other, right? But what if you want to pinpoint which device is really hogging all the bandwidth? That's where the Conversations window comes into play. In this window, you'll find a whole bunch of juicy details laid out neatly in columns. It tells you things like how many packets were sent and received, the amount of data transferred, the flow of traffic, MAC addresses of devices, and lots of other useful info. At the top, you'll see different tabs for various protocols, each with its own set of conversations. And next to each tab, there's a little number telling you how many unique conversations are happening. Now, let's say you're on the hunt for the device that's been churning out packets like there's no tomorrow. Just head over to the IPv4 tab, sort the packets column in descending order, and voila! The device listed at the top of the list is your culprit. So, in the Conversations window, you'll notice something interesting in the first row. It shows you exactly how many packets and bytes have been sent and received by each endpoint, along with the total elapsed duration. Now, if you're feeling particularly investigative and want to dig deeper, you can actually create filters right from this window. Just right-click on the first row and choose the option to create an expression. For example, let's say you're interested in seeing only the conversations between address A and address B. You can select the option A to B, and boom. It filters out all the packets associated with those specific addresses. So, it's like having a handy filter tool right at your fingertips, allowing you to focus on exactly the conversations you want to explore further. So, the Conversations window will let us collect and analyze details in a more granular form, which can be used in various scenarios while troubleshooting and auditing networking infrastructures. Now imagine you're overseeing this bustling network, and suddenly you notice a surge in traffic that's not quite normal. You're curious to know which devices are behind this unusual activity, right? Well, that's where the endpoints dialog comes to the rescue. So, what are endpoints? Well, they're basically the devices that share data with each other on the network. And to communicate, they need something called a MAC address. It's like their unique ID card. Wireshark lets us dive deep into analyzing and collecting info about these endpoints. To access the endpoints dialog, just click on any TCP packet in the packet list pane. You'll see a bunch of tabs at the top, each representing a different protocol. If a protocol is active in your traffic, its tab will light up, showing you the action. By default, you'll probably start with the Ethernet tab, where you can see the MAC addresses of the endpoints. Each tab also tells you how many endpoints are captured for that specific protocol. Pretty neat, huh? Now, here's where it gets interesting. You can dig into specific protocols by clicking on their tabs. For example, I clicked on the IPv4 tab and sorted the main pane using the packets column. This lets me see which endpoint is chattering away the most. But wait, there's more. If you want to analyze a specific endpoint even further, you can create a display filter for it. Just right-click on the row with the most packets transferred and choose Selected under Apply as Filter. Boom, now you've got a filter tailored just for that endpoint. And you'll find some handy checkboxes and buttons. You can use these to resolve the names of Ethernet addresses, limit the results based on a display filter, copy the content in CSV format, or even map the endpoint's location. So, with the endpoints dialog, you can quickly pinpoint the devices causing a stir on your network and dive deep into their activity with just a few clicks. Now packet length refers to the size of individual packets captured during network analysis. It tells us how much data is contained within each packet, including both the information being sent the payload and additional metadata, the header required for routing and processing the data. Understanding packet length is important for several reasons. It helps in monitoring network performance, identifying potential security threats, and ensuring compliance with protocol standards. By examining packet lengths, analysts can spot anomalies, such as unusually large or small packets, which might indicate issues like network congestion, malicious activity, or protocol violations. Alright, now let's talk about I/O graphs. These graphs are like snapshots of the traffic in our network. They help us see the busy and slow times, which can be super helpful for fixing problems or just keeping an eye on things. This graph shows time on the horizontal axis and the number of packets per tick on the vertical axis. If you need to adjust the scale, you can do that too. Now, looking at the graph, it's amazing how quickly we can gather this info from thousands of packets with just a glance at the graph. Below the graph, you'll find some tools and filters. Let's say we want to focus on just the UDP traffic and plot it with a red line. Easy peasy. We just type UDP in the filter box, deactivate graph 1, and activate graph 2. Voila! Now we have a graph showing only UDP traffic. Looking at this new graph, we can see that most of the UDP action happened. If we want to compare DNS and TCP traffic, we can do that too. It's like looking at two sides of the same coin. Comparing things helps us learn more effectively. Alright, let's see service response time. This feature is like having a stopwatch for different services or protocols. It tells you how long it takes for them to respond when they're pinged. So if you're wondering why a certain service is lagging or being sluggish, this tool can give you the scoop. It's like timing how quickly your favorite restaurant brings out your order. You want it fast, right? Similarly, in the digital world, we want our services to respond promptly to keep things running smoothly. Next, we have DHCP or bootup statistics. This shows us stats related to DHCP or Dynamic Host Configuration Protocol traffic. Basically, it's about how devices on a network get their IP addresses. Then there's net perf meter statistics. This probably has to do with measuring network performance. Moving on, we have ONCRPC programs. This provides information about ONCRPC Open Network Computing Remote Procedure Call programs, which are used for communication between networked computers. Next, let's talk about 29 West. This is a protocol or service that's often associated with messaging or data distribution. It's commonly used in financial markets and high-performance computing environments for fast and reliable data transfer. If my understanding of 29 West is incorrect, or if you have more information about it, please feel free to share in the comments. After that, we have a NCP, which stands for Access Node Control Protocol. It's used in broadband networks to manage access nodes. Then there's BACnet. BACnet in Wireshark refers to the BACnet or Building Automation and Control Networks Protocol, which is commonly used in building automation systems for controlling and monitoring devices such as HVAC systems, lighting, access control, and more. When you encounter BACnet in Wireshark, it means that Wireshark has detected network traffic related to the BACnet protocol. This traffic may include messages exchanged between BACnet devices, such as requests for data, responses, alarms, and other control commands. Analyzing BACnet traffic in Wireshark can provide insights into how devices in a building automation system communicate with each other, the types of data being exchanged, response times, error handling, and overall system performance. Up next is collecting. Oh, I never use this, so I don't know about this again. If you know about this, feel free to comment. Now we have DNS. This is the domain name system responsible for translating domain names like google.com into IP addresses. Alright, let's talk about FlowGraph. This tool is like your trusty detective when it comes to troubleshooting network issues. Imagine you're trying to figure out why your internet connection keeps dropping or why certain data isn't getting through. FlowGraph creates a visual summary of the traffic flow between two endpoints, helping you pinpoint where things might be going wrong. It's like drawing a map of the route your data takes from your device to its destination. With FlowGraph, you can quickly identify any bottlenecks or problems in the connection and get things back on track. Next, we have HART-IP. HART-IP refers to the Highway Addressable Remote Transducer over IP protocol. HART-IP is an implementation of the HART communication protocol, which is commonly used in process automation and industrial control systems. HART, or Highway Addressable Remote Transducer, is a communication protocol that allows digital communication with smart field devices such as sensors, actuators, and controllers in industrial applications. HART-IP extends this protocol by enabling communication over IP networks, making it more suitable for modern networked environments. HART-IP in Wireshark could include data exchange between devices, configuration commands, status updates, and other communication activities specific to the HART protocol implemented over IP networks. Analyzing HART-IP traffic in Wireshark can provide insights into the communication patterns, data payloads, error handling, and overall performance of HART-enabled devices operating in an IP network environment. It can be valuable for troubleshooting, monitoring, and optimizing HART-based systems in industrial settings. Then there's HP feeds. To be honest, I'm not too familiar with this one too. If you know about this, feel free to tell me on the comment. Today you are going to teach me, aren't you? Next up is HTTP, the Hypertext Transfer Protocol. This is what's used for communication on the web. Following that, we have HTTP2. This is a newer version of HTTP with some fancy features like multiplexing. Next, there's SAMA-time. SAMA-time is used for real-time collaboration and communication within organizations. SAMA-time is a messaging and conferencing protocol developed by IBM, similar to platforms like Microsoft Teams or Slack. When you encounter SAMA-time in Wireshark, it typically means that Wireshark has detected network traffic related to IBM SAMA-time communications. This could include messages, file transfers, audio-video calls, screen sharing, and other collaborative activities facilitated by the SAMA-time protocol. Analyzing SAMA-time traffic in Wireshark can provide info into how users are interacting, the types of data being exchanged, and any potential issues or optimizations related to SAMA-time communication within the network. Alright, let's dive into TCP stream graphs. These are basically visual representations of TCP streams, showing us how data moves over a TCP connection. To get started, just pick any TCP packet from your list and open the static view. When you hover over these TCP stream graphs, you'll see 5 options. Let's quickly discuss each one. First up is the time sequence graph. This graph gives us a chronological view of packets being sent and received, almost like peeking into a timeline of data events. Now, let's break down what you'll see in this graph. The x-axis represents time in seconds, while the y-axis shows the TCP sequence number. These sequence numbers increase with each packet sent, based on the data size. Looking at the graph itself, you'll notice 3 lines. The line labeled TCP data segment shows the actual data being transmitted. A longer line here indicates more data in that packet. Below that is the ACK stream, indicating acknowledgments for received segments. And at the top, we have the client receiving window, showing how much data the client can handle at a time. The distance between the client receiving window line and the TCP segment line is the window size. A closer gap means less buffering capacity, while a wider gap means more buffering. Moving on to throughput graphs, these show unidirectional traffic flow in bytes per second. Unlike I/O graphs that show traffic in both directions, throughput graphs focus solely on one direction. If you encounter a blank graph, try selecting another TCP packet to generate the graph. Next, let's talk about round-trip time or RTT. This measures the time it takes for an ACK to be received after sending a packet. Essentially, it tells us how long it takes for a sent packet to be acknowledged, ensuring successful delivery. Lastly, window scaling graphs illustrate how the size of data windows changes during transmission. It's akin to observing a mailbox's size as more letters are sent and received. These graphs provide valuable insights into TCP communication, helping us understand data flow and network performance better. After that, there's UDP multicast streams. Imagine you have a bunch of devices on your network, and you want to send the same message or data to all of them at once. That's where UDP multicast streams come into play. Think of it like a radio station broadcasting a song. Instead of sending the song individually to each person, the radio station sends it out once, and anyone tuned in can hear it. Similarly, UDP multicast allows one device to send data to a group of devices simultaneously. Now, when we say UDP multicast streams in Wireshark, it means we're looking at how this multicast communication is happening using the User Datagram Protocol, or UDP, which is a way for devices to send quick and simple messages to each other. When we use Wireshark to analyze UDP multicast streams, we can see exactly what data is being sent, who's sending it, and who's receiving it. This helps us troubleshoot any issues with multicast communication, like if some devices aren't getting the message or if there's too much traffic clogging up the network. Then, there's reliable server pooling. This is a protocol for setting up pools of servers that can handle requests reliably. Up next is SumIP. This is a versatile network protocol that excels in multitasking within the application layer. It efficiently handles message transformation, remote procedure calls, and service discovery in a dynamic client-server setup. Additionally, it's adept at managing large UDP messages without fragmentation, ensuring smooth communication between devices. Following that, we have DTN, which stands for Dynamic Trunking Protocol, is a protocol designed by Cisco Systems specifically for negotiating trunking between switches within a VLAN. Next, there's F5. This is likely related to load balancers or application delivery controllers, which help manage traffic on large networks. And finally, we have IPv4 statistics and IPv6 statistics. In Wireshark, the IPv4 statistics and IPv6 statistics provide detailed insights into network traffic specifically related to IPv4 and IPv6 protocols. These statistics include information such as packet counts, byte counts, and other metrics related to the utilization and performance of IPv4 and IPv6 networks. Analyzing these statistics can help network administrators understand the distribution of traffic, identify potential bottlenecks, and optimize network performance for both IPv4 and IPv6 communication. Alright, we're wrapping up here. If I missed explaining anything or if I goofed up somewhere, drop a comment and let me know. And hey, I'll admit it, I'm not perfect, so corrections are welcome. Now, buckle up because this video is your ticket to the Wireshark adventure. Remember, practice makes perfect, so don't just rely on this video. Dive into books, watch more videos, and soak up all the knowledge you can. If this video hasn't blown your mind yet, don't give up. Let's dive into some network analysis and wrap up this marathon of content before you start daydreaming about your next meal. Alright, let's delve into the world of TCP and UDP protocols, understand how they communicate, explore common issues, and discover how Wireshark can lend a helping hand. We'll learn how to analyze these protocols and spot any unusual behavior. But before we dive into the video, make sure you're familiar with TCP and UDP basics like TCP headers, various flags, and the TCP three-way handshake. If these terms sound like a foreign language, don't worry. Like I said at first, I've got a video dedicated to this topic that will provide a deeper understanding. The TCP three-way handshake is crucial as it ensures that both the server and client are prepared to establish a connection and have the necessary resources to maintain a dedicated channel for reliable packet delivery. Let's dive into a real scenario and witness the TCP three-way handshake in action using Wireshark. Firstly, let's gather some packets and filter for only TCP to focus on this specific protocol. Now, observe closely. The TCP handshake begins with the sender client initiating the connection by sending a TCP SYN packet to the receiver or server. The server responds with a SYN ACK packet, acknowledging the request and signaling its readiness to establish the connection. Finally, the client acknowledges this response with an ACK packet, confirming the connection setup. Voila! The TCP connection is established, and if you take a look now, you'll notice an HTTP GET request following the successful three-way handshake. Now that we've covered the TCP three-way handshake, let's explore another handy feature in Wireshark called Follow TCP Stream, or HTTP Stream, or UDP Stream. So, what does this feature do, you ask? Well, Wireshark allows us to reassemble a series of plain text protocol packets into a format that's easy for us to understand. For example, if we're dealing with an HTTP session, using Follow TCP Stream, we'll display the GET requests sent from the client and the corresponding responses received from the server. To access this feature, simply right-click, hover over Follow, and then select either HTTP Stream or TCP Stream, depending on the protocol being used. When dealing with HTTP, most of the content will be displayed in plain text, making it easier to analyze. However, if the protocol is HTTPS, where encryption is used, you'll likely see ambiguous text due to the encryption. Don't worry, we'll discuss decrypting HTTPS traffic in an upcoming video, but not now. The Follow TCP Stream option is incredibly useful for troubleshooting HTTP sessions, as well as other application layer protocols. In the dialog box, you can choose to view either side of the communication or the entire communication between the client and server simultaneously. Moreover, at the bottom of the dialog, there's a drop-down menu where you can select different formats such as ASCII, EBCDIC, hexdump, and C arrays. This allows you to view the data in various formats instead of just the raw data, making analysis more comprehensive and insightful. If you want to save the content shown in the dialog, then click on Save as then give it a name. Now it will save the content in a simple text format. Similarly, and if you want to view everything except the Follow TCP Stream packets that you are viewing currently, then click on Filter out this stream. To close the dialog, click on Close. Now I want you to imagine you're trying to communicate with a server, but the server daemon or the software running on the server to handle requests is not running. This means the server is not actively processing requests and cannot respond to your client's attempts to establish a connection. In such a scenario, your client will send SYN or synchronized packets to the server, indicating its intent to start a communication session. However, since the server is not available to respond, it sends back RST or reset packets in response to each SYN packet it receives. The RST packets essentially inform your client that the connection cannot be established because the server is not operational or reachable. When you analyze this situation using Wireshark, you'll notice a series of SYN and RST packets exchanged between your client and the non-responsive server. Each SYN packet represents an attempt by your client to establish a connection, and each RST packet signifies the server's inability to respond, leading to the termination of the connection attempt. It's important to note that modern web browsers often attempt multiple connections to a server when faced with a non-responsive or closed socket. This is why you may observe multiple SYN and RST packets in Wireshark, corresponding to the browser's repeated connection attempts at specific intervals. One of the common scenarios that falls under this category is the situation where a connection is lost or an unsuccessful connection attempt is made, as we've previously analyzed in the section about RST packets. However, there are several other examples of network issues that you might encounter and need to troubleshoot using Wireshark. For instance, high latencies can occur due to long-distance communications or when traffic gets queued up, causing delays in data transmission. To analyze and identify such problems effectively, you can utilize the time column in Wireshark by sorting it. This allows you to easily spot large time gaps between packets at the top of the list pane, indicating potential latency issues. Another example scenario involves a malicious user attempting a port scan on your network. In response, your firewall may send RST packets to the user to thwart the attack, or because the targeted port is closed. A port scan generates a significant amount of traffic, which can be observed as noise in the Wireshark list pane. Now I am demonstrating a port scan initiated using NMAP from another device. Our machine responded with RST packets because the scanned port was closed. This interaction between the scanner and our machine provides valuable insights into potential security threats, highlighting the importance of monitoring network traffic for anomalies. Additionally, Wireshark allows you to analyze various connection behaviors, TCP headers, packet flags, and sequence acknowledgement or SecAC numbers. With a clear understanding of these fundamentals, you can easily detect and investigate unusual traffic patterns that may indicate network issues or security threats. It's essential to note that while Wireshark provides powerful analysis capabilities, there is no automated tool that can automatically detect and alert you to all traffic anomalies. Customizing your environment and staying vigilant during network monitoring are crucial steps in ensuring the security and efficiency of your network operations. While we've covered some aspects of TCP analysis here, it's important to note that this isn't an exhaustive exploration of TCP analysis. There's a wealth of information and techniques related to TCP and other protocols that can be explored in much greater detail. If you're interested in delving deeper into the analysis of specific protocols using Wireshark, such as TCP, UDP, HTTP, and others, I can create dedicated video tutorials for each protocol. These videos would provide a comprehensive understanding of how to interpret and analyze protocol-specific data captured by Wireshark. So, if you're interested in a comprehensive exploration of protocol analysis using Wireshark, let me know, and I'll be happy to create these informative and engaging video tutorials for you to further enhance your skills and understanding in network analysis. Now, let's delve into a brief overview of UDP or User Datagram Protocol. UDP is a connectionless protocol known for its efficiency in transmitting real-time data between hosts. It's often referred to as an unreliable form of communication because it doesn't ensure the delivery of packets. In UDP, any lost packets are not retransmitted, as the sender is not informed about dropped or discarded packets during transmission. However, several important protocols like DHCP, DNS, and others rely solely on UDP. Protocols that utilize UDP as a transport mechanism must employ other techniques to ensure data delivery and error checking capabilities. Despite its lack of reliability compared to TCP, UDP offers faster transmission of packets. Unlike TCP, UDP doesn't involve the initiation of connections or graceful terminations, which is why it's also known as a transaction-oriented protocol rather than a message-oriented protocol like TCP. To understand how UDP functions, let's examine some protocols that use UDP as their delivery protocol. First, we'll discuss DHCP, followed by an analysis of DNS traffic. The Dynamic Host Configuration Protocol, or DHCP, is a crucial protocol responsible for assigning IP addresses to devices and ensuring their compatibility within a network. In typical network configurations, the DHCP server operates on port number 67, while the DHCP client communicates through port number 68 by default. One key aspect to note is the packet length field. This field specifies the overall length of the packet from the first byte to the end of the data contained within it. Within a packet of, for example, 308 bytes, 8 bytes are allocated for the UDP header, leaving 300 bytes for the application data that follows. When a device undergoes a power cycle, it initiates a DHCP request to the DHCP server to obtain an IP address. This action generates several packets related to the DHCP process, including requests, releases, offers, and other associated communications. These packets utilize UDP as the transport mechanism for their transmission within the network infrastructure. Analyzing DNS or domain name system traffic in Wireshark based on UDP involves examining the packets exchanged during DNS queries and responses. Here's a step-by-step guide on how to analyze DNS traffic using Wireshark. Open a web browser or any application that generates DNS queries. Enter a domain name in the browser's address bar, for example, com, and press enter. This action triggers a DNS query to resolve the domain name into an IP address. After performing the DNS query, return to Wireshark and stop the packet capture by clicking on the red Stop button. Apply a filter to display only DNS packets in the captured traffic. Enter DNS in the display filter bar and press enter. This filter will show only DNS-related packets. Look for DNS query packets, typically with a DNS query transaction ID in the captured traffic. These packets indicate the domain name being queried. Locate DNS response packets corresponding to the DNS queries. These packets contain information such as the resolved IP address of the domain queried. Select a DNS query or response packet, and in the Packet Details pane, expand the Domain Name System section to view detailed DNS information. Analyze fields like query type, query name or domain name, response type TTL or time to live, and answer or resolved IP address or other records. Pay attention to DNS flags such as query response, recursion desired, recursion available, and response code. These flags provide insights into the DNS transaction and any issues encountered. Use Wireshark's Follow feature to track DNS transactions. Right-click on a DNS query packet, select Follow, and choose UDP stream or DNS. This view helps in analyzing the complete DNS conversation between client and server. DNS responses may include additional records like NS or name server, CNAME or canonical name, MX or mail exchange, and text records. Examine these records for comprehensive DNS analysis. I hope you've gained a basic understanding of Wireshark from this video. However, I want to acknowledge that this video isn't a comprehensive guide on Wireshark. Unfortunately, I'm limited in time as I'm also creating a course and have a busy schedule. However, I'll do my best to cover each protocol in Wireshark in future videos. If you're interested in overviews of other tools or topics, please leave a comment below. Thank you for watching, and if you're eager to delve deeper into cybersecurity and hacking techniques, consider subscribing. If you want to see our NMAP full guide, click this. See you next time.